This is Professor Stephen Sekula from Southern Methodist University, and I'd like to welcome you to the first part in a two-part lecture on electric fields and energy. Now, previously in this course, we've been talking mostly about force. This is the way that many physics courses start out. They introduce the concept that there is matter, that matter responds to force, for instance, something pushing on it, something pulling on it, and that response is encoded in Newton's laws. For instance, Newton's second law of motion says that if there is a force acting on an object with mass m, it will accelerate, F equals ma. But fundamentally, in physics, what we're really talking about is the storage and transfer of different kinds of energy from one into the other. And there's a guiding principle in the universe that we have really never seen a violation of in any experiment that's ever been conducted. And that is the principle of the conservation of energy. It's really a foundational idea of nature. In every interaction that occurs in nature, for instance, matter interacting with other matter through forces and exchanging energy, the total energy in the system is always conserved. So if we have some initial energy in a closed system, that is a system free from external influences but which can interact within itself, the initial energy of that system will always be equal to the final energy of the system. Now you have to be a little bit careful. Energy takes many forms. Some very familiar forms are kinetic energy, potential energy. For instance, the energy of a ball that is held up high above your head in a gravitational field. That's storing energy in the gravitational field because the gravitational field wants to pull it down closer to the center of the Earth. There's also heat. This is the energy of vibration inside of a material. Think of all the many atoms in a material all vibrating very rapidly. This can cause the emission of radiation, and this is what we know of as heat. Light, which is basically visible radiation. This is another form of energy, and there are many other kinds of energy that are maybe less familiar. But if you take account of all of these in a system, then you will find that the initial energy of a closed system, free from external influences, but which is free to interact with itself, will always be equal to the final energy of the system. Kinetic energy, which is often written as Ke, is the energy of motion, and it's equal to 1/2 of the mass times the speed squared of the material. So for instance, if we have an electron and it is moving at a speed of, say, 25 miles an hour, we can take the mass of the electron and we can calculate its kinetic energy. Potential energy is important, but perhaps a little more mysterious. The simplest definition of potential energy, it is the energy of configuration. Again, I go back to the image of take a ball, place it on the ground. Now, let's consider that to be the 0 point of the potential energy of the system. That is, the potential energy of a ball will be considered to be 0 when it's on the ground. Let me sketch this here. Here's the ground, here's a ball. And now you lift the ball up in the gravitational field. Gravity wants to pull down on the ball and pull it back to the Earth, but by doing work on the ball, you have done work against the gravitational field, and you're effectively storing energy in the configuration of the ball. That is, by raising it to a height h above the ground, you give it a potential energy, which we'll call u, and that is equal to mgh, the mass of the ball, times the acceleration due to gravity, times the height above the ground that you raise the ball. This should be a familiar example from mechanics. If it's not, go back and review it. Let's focus a little bit more on potential energy for a second, because in the coming discussion regarding energy and electric fields, it's very important to understand potential energy, and particularly differences in potential energy between 2 points. To begin, let's remember the concept of work. Work is when a force acts over a path. So for instance, imagine we have a force field, like gravity. Here I draw the lines of force pointing down. Here's the force due to gravity. And we have a point up here, A, and a point down here, B. Now, imagine that you have an object that starts out at point A, and it's going to take a path from point A to point B. Now, if it's free from other things, gravity will simply pull the mass at point A down to point B. That's one path that this thing could take through the gravitational force field. Now, on the other hand, you could give it a little help, and you could maybe move the object down toward point B by some wiggly path. The idea of work is that work done against or by a force, like for instance gravity, the total work that you do, or that the field does, is equal to the integral from A to B of the dot product of the force and a piece of the path dr vector. Let's take a look at our path here. Let me zoom in on our little path. Here's a squiggly piece of the path. We've maybe zoomed in on some piece of this. And we have at every point here force pointing down. This is our gravitational force at every point on the path. It's always acting down, 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 down. Okay, it doesn't matter where you are on the path. That's what gravity is doing. It's trying to pull you down. Now, the work that you do with or against gravity, let's say in this case the work done by gravity, because we're being pulled from high to low, and gravity wants to pull you from high to low with respect to the surface of the Earth, the work is going to simply be equal to the product of the force and a little vector dr that is tangent to every point on the path. And depending on where we are on the path, we have different tangent vectors that point in the direction that we're moving on the path. So here are a bunch of little tangent vectors, dr vector, at each point on the path. And the work is the product of these two vectors, the force field and these little dr vectors, summed, or in this case integrated, because they're tiny little pieces, over the whole path going from point A to point B. That's the definition of the work. And to be very specific, this is the work that is done, for instance, by the gravitational field moving a mass from point A to point B. Here's the thing. Any component of the path that is perpendicular to the force does not contribute to the work. So for instance, for every little horizontal motion along this path, that little horizontal motion doesn't involve any work being done by the gravitational field or being done against the gravitational field if you're pushing the mass upward. Let's remind ourselves of the properties of the dot product. The dot product of two vectors, A vector and B vector, will give you a number, C. Not a vector, a number. If you want to get a vector, you need to use the cross product. The magnitude of C will be equal to AB times the cosine of the angle between A and B. So for instance, if this is my A vector and this is my B vector and this is theta, the angle between them, the magnitude of C will be equal to the magnitudes of A times B times the cosine of the angle theta between them. What happens if theta is equal to 90 degrees? That is, what happens if you have a piece of your path which is itself perpendicular to the force vector? Well, then cosine of theta is equal to 0. And you see immediately that any component of dr vector that is perpendicular to the force field will not contribute to the work. So gravity does no work if the object moves to the sides. And you do no work against gravity if you lift the object up and wiggle it back and forth side to side as you move it up. The only part of the work that matters, let's say you doing work against gravity, the only part of the work that matters is the part of your path that is parallel to the force field, either with it or against it, but parallel to it. Okay, so that's a quick review of work. Now, how does that relate to potential energy? Well, let's imagine that you start out at a high point. So here's a high point A, and here's a low point B. And again, here's the direction that the gravitational field points. What is the work done from A to B by gravity? Well, let's say here's our path, and every vector along the path points in the same direction. It's a straight path from A to B. The work done by gravity from A to B is just going to be the integral from A to B of the gravitational force dotted with dr vector. And since gravity and dr vector are parallel to one another, then this will just be the integral between A and B of the magnitude of the gravitational force times dr times cos theta. Theta is equal to 0, so this is just equal to 1. Now let's think about potential energy. What is the relationship between the potential energy at point A and the potential energy at point B? How do they relate to one another? We say that something has a high potential energy if gravity wants to pull it down to a lower point. So for instance, in this picture we have a point A that is above point B. Gravity acts down, and so the potential energy of point A will be greater than the potential energy of point B. So if we think about the change in potential energy from A to B, which we can define as the difference in the potential energy at B and A, we see that if the potential energy at A is greater than the potential energy at B, then we have a number which is less than 0, because B is smaller than A, and when you subtract A from B, you get a negative number. But the work that's being done by gravity is positive. By conservation of energy, the energy stored in the gravitational field is released when gravity does work on the object and pulls it from high to low. But we know that that's less than 0. But the work must be equal to that, or related to that, the work done by gravity to release the potential energy and get the object down to a lower potential energy. That's a number which is greater than 0. And so what we find is that the relationship between the change in potential energy between 2 points A and B and the work done by the force, in this case gravity, it's the negative of the work. It's the only way that conservation of energy can work out, and you can get all the signs right. This is a bit subtle, so think about it this way. If you're going from a point high above the ground, high potential energy, to a point closer to the ground, lower potential energy, the difference in the potential energies of the two locations is going to be the energy released from the gravitational field. But because of this definition, that potential energy change is negative. The work done by gravity, however, is positive because it points in the same direction as the path. Gravity's doing work on the object, and by doing that, it's releasing potential energy. And so, work must be a positive quantity. Conservation of energy demands that the work done by the gravitational field and the change in the potential energy have to be directly related to one another. And the only way that can be satisfied is if their relationship involves a minus sign. So we have now a very useful definition. The change in potential energy between any 2 points, A and B, is equal to the negative of the work, say, done by the force between A and B, and that must be equal to the negative of the integral from A to B of f dot dr vector. So this is a very general relationship. We've been thinking about this in terms of gravity, but it doesn't really matter what this force is, and it doesn't matter what this path is that's being taken through the force field. That will be related to changes in potential energy. Now, a key thing about potential energy. There is no such thing as absolute potential energy. What do I mean by that? What I mean is that potential energy is only defined with respect to something. So for instance, I can choose that the ground be the 0 of potential energy, and that all changes in height relative to that are changes in potential energy relative to the ground. On the other hand, I could do all my experiments on the top of a very tall building, and for convenience, I could define the roof of the building to be the location of zero potential energy, in which case, if in a gravitational field, gravity pulls an object below the roof of the building, it actually has negative potential energy. That's totally okay. Potential energy is a relative concept, and all the signs work out in conservation of energy. It doesn't matter where you define the zero potential energy, so define it to be in a convenient location. This will come in handy in solving problems involving electric fields. So let's introduce electric fields into this discussion. Let's talk about potential energy and electric fields. We know that the force that an electric field exerts on a charge Q is just given by the product of the charge and the electric field vector. That's just an inversion of the definition of the electric field, which is the force per unit charge. So that means that changes in potential energy in an electric field will be equal to the negative of the work done by the field, and that's going to be equal to negative the integral from a to b of f dot dr vector, but f in this case is q e vector dot dr vector. And again, where dr vector represents pieces of the path. It doesn't matter what path you take, we discussed that already, because any part of the path that is perpendicular to the electric field doesn't count in the work anyway. So you could take a straight path through the electric field, you could take a wiggly path through the electric field. All that matters is the component of the path along the electric field, and that always has the same length. So this is our relationship between changes in potential energy, let's say for an electric charge and an electric field between 2 points A and B, A and B, and I have some charge Q that's moving on a path between these 2 points. The change in potential energy is just equal to the negative of the integral of the product of Q, the charge, the electric field direction between points A and B. So we can imagine that this is some kind of uniform electric field, for instance, here. And the pieces of the path dr. And again, the only pieces that matter are the ones that are parallel to the electric field, E vector. Alright, here's the catch. Unlike in gravitation, where there's only mass, which is sort of the charge of gravity, in electric fields there are 2 charges. Mass is always positive, but electric charge can be positive or negative. So here's what I want you to think about. Let's imagine we have a situation with a uniform electric field, and just in case it's hard to see, the electric field vectors all point down like this, and they end down at the bottom on this line here. Okay? So we have an electric field, it's uniform, it points down. We have 2 charges. Charge 1. Charge 1 has a charge that's less than 0, so it's a negative charge. Charge 2 has a charge that's greater than 0, so it's a positive charge, and their magnitudes are the same. So all that differs between these 2 charges is their sign. One is positive, one is negative. Okay? Here's the question I want you to answer for the negative and the positive charge. Relative to this bottom line down here, are these charges at different potential energies? And, if the answer is yes, which one is at a higher potential energy and which one is at a lower potential energy? Now keep in mind that an electric force field is going to have a high potential energy relative to a location where the charge wants to be in that field. Okay, so let's take the positive charge as an example. Ask yourself if charge 2 is at a higher electric potential energy than it would be if it were down here on this line at the bottom. Okay, and you can use the analogy of a ball in the air and then suddenly letting the ball go. It's going to go to a location of lower potential energy. That's where the gravitational force wants to take it. Now think about the electric force acting on a positive charge and acting on a negative charge. What direction does the electric field want to take the positive charge? That's the direction of decreasing electric potential energy for the positive charge. What direction does it want to take the negative charge in? That's the direction of decreasing potential energy for the negative charge. Okay? So what I want you to do is think about this question. I want you to pause the video here and think about this before proceeding. Okay, so you've had some time to think about this. Here are the charges again. Here's the negative charge. Here's the positive charge. Let's look at the positive charge first, because this is a lot like the gravitational force field. You have an electric field that points down. The positive charge feels a force that points down as well. That must mean that here, the potential energy is greater than it is down here. So let's define the ground, or this line down here, as being potential energy 0. And let's define this as the location of the second charge, 2. And so it has a potential U2, and U2 is greater than U ground. Okay, because the positive charge, when free to move under the influence of the electric force field, will move down. And it's moving toward a region of lower potential energy. That's the definition of when a field does work on an object, it's moving it toward a location of lower potential energy. What about the negative charge? Well, electric field points in the same direction, but the force on the negative charge points in the opposite direction. So again, if we have U ground down here, and that's equal to 0, this electric charge is attempting to move up. And so if we write the potential energy of this location as U1, what we find is that U1 must already be a lower potential energy than U ground, because the charge wants to move this way, above U ground, to an even lower potential energy. And so if we combine these two inequalities here, what we find out is that U2 must be greater than U1, even though they're at the same height above this line at the bottom. And that's, again, because of this quirky nature of the electric force. It has two charges that it can act on. Negative charges move against the field, positive charges move with the field, and as a result, what is a high potential energy may be a low potential energy location for the other. Okay, some food for thought there.